Test will be returned at a later date, not tonight. Definitely by Tuesday. I'm not sure. We'll see. Not today, definitely by Tuesday. The key is now posted. Third floor in the glass case. I will be passing back my lab's bromination report here in class at the end. If I forget, please remind me. Okay, 2 tests down, 1 to go, followed by a comprehensive exam. Don't forget what you knew for test 1. Don't forget what you know right now for test 2. And we have test 3 material. Looks like it's the bottom of the hour. We get started. Have a gold sheet. First topic for test 3 is resonance. I can say a couple of things. There's a seminar tomorrow in this room. It's a physicist from Clemson. Dr. John Marler from Clemson talking about some physics tomorrow. Highly charged particles, or highly charged ions, at 1 o'clock right here in this room. Next Tuesday, we're trying to give away $15,000, $16,000. Anybody interested? Okay. If you're interested in teaching science or mathematics as high school, we do have a program where you get your BS and MAT in just 5 years, Masters of Arts in Teaching. We have a scholarship program for this. It's called the Prestige Program. This is some current Prestige scholars. There's an information session next Tuesday at 1 p.m. I think it's right across the hall. If nothing else, come get some pizza and a drink. If you want one of these nice brochures, you can pick one up on the way out. Seminar tomorrow. We're going to begin resonance. We talked about resonance a little bit. Here's a little cartoon. The instructor says define resonance, and they say, sure, that's where you live. No, that's residence. I think it was funny. No, they didn't get it either. Resonance. Not residence. Okay. Something for your refrigerator. Everybody got a gold sheet? So, Dr. Panda. Dr. Panda, go. I got plenty of it. I need one more.
I'll give you mine back when you
do. Next time I only may have one extra.
I have one at home, but I left upstairs, so I'll just give you that one back.
Okay, resonance can be found in chapter 2. A lot of books cover resonance very early on. I kind of just give you a glimpse of it. I think it's too early to really dive into it too deeply. We see enough for what we need. We actually have resonance in our tautomerization mechanism. Okay, Oreo. Here we go. Also known as delocalized bonding. Let's start with neutral conjugated alkenes. Hopefully you can see this. Is that better? I put it on gold because really it's sort of the, if you learn and master resonance, it'd be gold. Golden. We also have the golden rules. On the back sheet, there's some golden rules to resonance. So usually I put these on gold. Neutral conjugated alkenes. First off, we can look at these two compounds here. They both have two alkenes. They're called dienes. We have two enes, it's diene. If there were three enes, it would be a triene, etc. Okay? Two different dienes. This one's called conjugated. That one's non-conjugated. All right? Which one's more stable? We have heaps of hydrogenation given. That indicates that which one's more stable. Ah, this one's more stable. It has a lower heat of hydrogenation. It means it gives off less heat when it's fully hydrogenated. Okay? That one must sit higher in energy to give off more heat. Why is this one more stable? Because it's conjugated. But that doesn't answer the question. Why is conjugated make it more stable? You got to remember, if somebody asks you why Bill Gates is rich, the answer is not because he has lots of money. Then I got to turn around and say, well, why does he have lots of money? Okay, you got to explain the deeper question. Why is this more stable? It's resonance. Okay, we have if we draw this structure and put in the p orbitals. Okay, there's there's pi bond on the end, and we also have pi bond here. Yeah. But you got to know hybridization, you got to know p orbital, okay? We did all that during test 1. And that's what we got here. But what you don't see from that structure here, because this structure has limitations, it doesn't show the full gist of what's going on. Between carbon 2 and 3, there's also pi overlap. Why wouldn't there be? You got how many electrons in each p orbital here? 2 in each p orbital?
No, 1 in each.
1 in each p orbital. Overlapping. Okay. Pi bond, pi bond. Are you telling me that these two are not overlapping? Or are they?
They are.
They actually also are. There's overlap there as well. We don't see that here. It looks like it's not. You have to just know that overlap is there. What we have here is we have an extended conjugation. When you overlap p orbitals, it's called conjugation. Now you can call that conjugated, but typically you don't say it's conjugated until you get like 3 or 4. It could be 2, but you usually don't call an alkene conjugated. But now we've got 4 conjugated. It's important to know how many electrons are in your pi system. We got 4 pi electrons. They're pi electrons because they're in p orbitals. Okay, we looked at that during test 1. How many p orbitals here? 4 p orbitals. Okay, so this is what I call the pi system. And they're all conjugated. If we look at the other one, well, I'll do it right here. We have p orbital there and p orbital there. Is there a p orbital here? No, that's sp3, no p orbital. And so you've got 2 isolated alkenes. Is there any overlap between this p orbital here and here? No. It's going to have to be something quite unusual for that to be overlap. But typically for us, no, it's got to be adjacent to each other. Not only does it have to be adjacent, later on we got to see they have to be parallel. Okay? Just because they're adjacent don't mean they're overlapping, right? Like we saw that before. 2 isolated alkenes, non-conjugated. That's why it's called a non-conjugated diene. You don't have the additional p orbital overlap that you have here. P orbital overlap is a good thing. It lowers the stability. It lowers the energy. It increases the stability. Okay? Makes it more stable. You don't have that extra stability there. We see that in the heats of hydrogenation number. On the right here, this is not a conjugated diene. That's called accumulated diene. Those double bonds are not conjugated. This comes from understanding structure. What's the hybridization of the middle carbon? SP. Right? 2 electron regions. That means the middle carbon has how many p orbitals? 2. It's overlapping with the next door carbon that has 2 H's. The next door carbon is what hybridization? sp2, trigonal planar. That's why I drew it trigonal planar with the p orbital. Okay? Now if we draw this one over here, the important thing here, how is the other p orbital on the center carbon? Is it straight up and down like this one, or is it out and back? That's perpendicular, also called orthogonal. It's out here. Now, it's hard for me to draw that. I wish I had just something I could just stick there. It's half on this side, half on the other. This one. Now, the important thing is, since that one's like that, how do you think this one is? It's the same way. What you have here is, those 2 are like that, but these 2 are like this. And that's actually, if we drew this over here, if the p orbital is straight up, these are actually like this. Like we turned it, like we turned the alkane like we did reactions. It's like that's flat, the p orbital is straight up. Okay? P orbital is like this, but if we draw it straight up on the board, then that's flat. Actually over here, it's not. Because here the p orbital is coming out, that means the rest is flat. So that's all planar. These 2 are not. And I'm not going to draw on these p orbitals. But these 2 p orbitals are not overlapping with these 2. Certainly this one is not overlapping with that one. It's 2 separate, accumulated is 2 separate alkenes, just like the middle one. That makes sense if you understand structure? So, a lot of students are quick to say, hey, conjugate it because they're close together. No. The granddaddy of all conjugated systems is the benzene ring, typically drawn here, here, here. All right, if we draw in p orbitals, boom, boom, overlap there. It's hard to make sure these are all planar. Overlap there, overlap there. See, that ended up being turned. It looks like that's not going to overlap. There's overlap between here, there's overlap between here, and there's overlap between there. There's actually overlap the whole way around. A lot of times people will just draw benzene with just a circle, because it's high overlap all the way around in there. You just have to know that. When you draw resonance structures, this ends up being sort of a hybrid. We'll get to that, but that is a fully conjugated cyclic system, and that's the definition really of aromatic or anti-aromatic. But we'll cover aromaticity in organic too. Okay, so we can see the results of this. This is empirical evidence for conjugation. Conjugation is a good thing. Okay, let's look at resonance structures. As we go through this, there's going to be sort of 2 approaches. One's going to be theoretical, okay? And part of theoretical is understanding the structure. Then the other thing we're going to need to learn how to do is just how to draw resonance structures. How to just do it on the board, and okay? Showing dipolar resonance structures of start with this guy. It's a little bit tough to start with this guy, and it's pretty much what we did up there. I mean, the only difference between this and the conjugated diene is just an extra methyl. So I've really already talked about the theory. Let's just show resonance structures like it says. pi bond can be polarized. And pi bonds are known to be more polarizable than sigma bonds. For example, we can move these electrons and just do this. I'm moving the pi electrons just back to the carbon. What does that give? It's going to give, really, what does this arrow mean to you? Electrons moving back to carbon, and so we've got, what now on this carbon? A lone pair. 2 pi electrons, we're just moving them to the carbon, and that is a minus. Because there is 2 H's there, okay? We learned how to do charge back there in week 1. But what is here?
Plus or both?
A plus. How many H's there? Only 1. Okay, there's only 3 bonds there, that's a plus. So we just polarize the pi bond by moving the electrons one way. Now we could have did it the other way. What you don't have here is you don't have a heteroatom which you move electrons towards. So it's not as easy to show this. But that's a resonance structure. Why is it a resonance structure? Because all we've done is move pi electrons, right? When all you do is move pi electrons, we call that a resonance structure. This is a resonance arrow, double-headed. So use appropriate arrow. This is a resonance structure. Now, on day 1, we may have drawn Lewis structures. And if we had this, we would have said this needs another bond. What would we have done? We would have moved these in. And if we do that, what do we get? We get back over there. So I just went the other way. I polarized it. So wouldn't worry about that. Can we show another resonance structure?
Yes.
Let's do a little bit of theory. But we could just pass over this theory. Let's do this at least once. Really theoretical. Tell me about the pi system. How many p orbitals are we dealing with? How many conjugated p orbitals? 4. How many electrons in the pi system? Okay, that's just like the one above. Don't be quick to write this down. Let me show it to you. Let's see if you want to write it down. I just want to give you some theory. Let's put these p orbitals here. How many electrons we got to put in there? 4. Put them any way you want, and that'll be a resonance structure. Really what you have here is these 4 electrons are spread out through here. They're distributed in there, just as opposed to 2 and 2. It's almost kind of like this. I'll give you a silly analogy. If I took a garden hose that was 4 foot long, and I put 4 liters of water in it, if that would even fit, what would the water do if I laid the garden hose flat? Tied off each end. The water would spread out all on the garden hose, right? Does that make sense? What if I lifted one end of the garden hose up? What would the water do? Flow towards the other end? Because of gravity? That's going to be analogous to us putting a heteroatom in. If we put a heteroatom, which is electronegative, it's going to attract the electrons towards it. So the electrons would flow towards the heteroatom. Once you get resonance, the electrons are just sort of in here. These become fake structures. But it's hard to show that. What you really have is electrons all the way through there. To get a resonance structure, you can just draw this and say, okay, 4 electrons. I'm going to put 2 here, 1 there, 1 there, 1 there. That's a resonance structure. Okay. There we go. Only 4. We got to keep track. That's a resonance structure. Now, if I drew bonds, that looks like a pi bond. That's going to be boom, boom. Pi bond here, because 1 electron, 1 electron. What would be here? Lone pair, what would be here? No electron. So that would be plus. That'd be minus. Man, that's a resonance structure. You can show it any way you want. You could even start maybe showing, well, if I did that, that's the original, isn't it?
Yeah.
Yeah. What do I have up there? That's where I got 2 here, none there, 1 and 1. You can sit down and put them any way you want. They'll all be resonance structures. Now, that sort of theory. Here is how we kind of need to do it on paper to kind of keep track. Let's go back up here. From here, I have a plus. Common resonance is, think about, how do you stabilize a plus?
Minus.
Do you move electrons towards it or away?
Towards it.
Towards it. We can move these towards it, but that would give this. What else could we move towards it? How about if we swing this double bond over? I'm going to call that like a windshield wiper. What does that air movement give? Resonance arrow. I now have double bond in here. We didn't do anything over there. And what's here now?
Positive.
Positive. There you go. We just got another resonance structure. Understanding how do you stabilize a plus? Move electrons towards it. I bond can swing towards it, long pair, but that would go this way. Could you do others? You could. You could polarize this here and make plus minus there, then you're getting lots of charge. While it is a resonance structure, we want to keep our charge limited. Things we will ask. First off, some golden rules. Question?
Wouldn't that one to bond around itself?
This here? Okay, what would that do? You got some bad bond angles there. I don't know if you can make a bond. But let's assume it did. A long bond. What type of bond is this? Pi or sigma? It's a single bond. See, that's a sigma bond. And anytime you do resonance, you're only dealing with pi bonds. This is no longer the same compound. You have done a reaction and made a new compound. This is not a resonance structure. No sigma bonds. One of the first golden rules, or one of them, is only move pi electrons. It's a pi electron there, but when it bonds, it becomes sigma electrons because this is going to become sp3. They both become sp3. Let's look at the golden rules. Is there another handout? What's the first golden rule?
Only move pi electrons.
Only move pi electrons. Don't go moving any sigma electrons. All right? Pi electrons. These are pi electrons here, but when you make a sigma bond, you're kind of violating the rule a little bit. You don't want to make a new compound. What did we get back? Let's go back to where we were. We had minus, plus. What's second golden rule? Don't move any atoms around either.
Yep.
And going from here to here to here, did we move any atoms?
No.
No. All I moved is pi electrons. Golden rule number 3. Often forgotten about, or all resonance structures have same net charge. What's the net charge of the starting one?
0.
Neutral. That's 0. What's the net charge here?
0. 0.
Yeah. See, a resonance structure is just a different depiction of the same thing. This is a little bit tough because there's no heteroatom. Let's say a couple of other things. Let's go back to the front, a comment on hybrids, true structure. Okay. Basically, the electrons are spread out all the way through there. And the true structure often can be shown sort of like this. How did I get there? I've got three structures on the board. Take a look at here. Here I have a double bond between these two carbons. Double bond, but there I have single. So all these structures contribute to the true structure. This tells us that the true structure has not fully a double bond here. It's got some single bond character. Now it has more double bond character because we see two here. It's like making a milkshake with 2 scoops of chocolate and only 1 scoop of the milk. The milkshake is going to be more chocolatey, more double bondy than single bond. When we start drawing hybrids, it's hard to do that. And usually you just show that it's bond and a half, that it's somewhere between 1 and 2. And you're never going to say, well, it's really closer to 2. You just don't, it's hard to do that. This indicates that the BO is 1 to 2. What is BO? Bond order. Bond order for double bond is 2. Bond order for a single bond is 1. This is somewhere in between 1 and 2. If we just look at this structure, we would say BO equals 2, 2, and BO equals 1. But that's not right. There's actually some pi bonding between 2 and 3, as we showed already. That's additional bonding. We also see that here in this hybrid. Between 1 and 2, it's sort of like this, all the way across. We'll do more of this. Again, this is a difficult example. The main reason is, another thing we'll do is say which resonance structure is your major one, your best. Of the 3 here, which one's best?
The first one.
The first one, yes. Why? Because there's no charge separation. Okay? Polarizing, making charges is not going to be your best resonance structure. Now, last comment here. Ultimately, the true structure is these electrons are spread out through here, but they look more like, the true structure looks most like which one of these? Most like that, but it has character, some character like this also. We'll say the same type of stuff in other examples, and hopefully it'll become more clear as we do it again and again. Oh yeah, partial charges. This is just tough to show partial charges. I'm not going to show it here. It's net neutral anyway. It's hard to show there because there's no heterobound. Let's go below. Some things will be easier once we move down to a cation. Resonance stabilization of cations. Okay, we got this original cation here. How do you stabilize cation?
Move the electron.
Move electrons towards it. We've already done that once, so go ahead and draw a resonance structure of that cation. Here we go. Like a windshield wiper with this type of example. Let's move the pi bond over. What do we get? And now the plus is there. There you go. Move pi electrons, we'll get that. We can ask, which resonance structure is major? Which one do you like better? Which one's more stable? They're the same. Yes. We call this equal contributors. And what's the hybrid going to look like? The hybrid, we can do this. See, this is a better example for doing the hybrid because we got two equal contributors. What's the BO between, let's call that 1, 2, and 3. What's the BO between 1 and 2? Well, here we got single bond. Here we got double. They both contribute, so what's the average of single and double? 1.5. So I can draw that like a bond and a half. On the other side, double there but single here. What's the average of 2 and 1? 1.5. Now we can do charge. Here carbon 1 is plus, here it's neutral. What's the exact average of plus 1 and neutral? Yes, we're going to say partial plus, but it's actually exactly 0.5, that's half the charge. Does the second carbon have any charge? Neither resonance structure shows charge there. How about the third one? Neutral, positive, what's the average of that? Yes. Can you see there? I need a darker pen. So this is our hybrid, resonance hybrid. Which bond is longer, 1, 2 or 2, 3? Look at this here. Which bond is longer? They're equal. They're equal. And see, if you didn't know resonance, you would say, well, single bond is longer than pi bond. Yeah, but we've got resonance going on here. And the true structure is the hybrid, and they're equal. They have the same bond order. It's equal bond lengths. Okay? Equal bond lengths here. Which carbon has more charge, 1 or 3? If you didn't know resonance, you'd say, well, it's 1. But you got to know resonance, and really the charge is spread out, and you got equal charge of both 1 and 3. And then we can say a term like delocalized. Is the charge localized on 1, or is it delocalized over 1 and 3? Charge is delocalized. See, this is a perfect blend. Neither resonance structure is major. Now I could draw another resonance structure. I could polarize this. Seems like they're all kind of... I polarize that. What does that give? It's going to give that. Wouldn't it?
Yeah.
See, I wouldn't even recommend drawing that resonance structure. That's just so bad. Very often we'll say, draw a resonance structure that, to delocalize this charge. Doing that doesn't delocalize that charge. It just creates new charge. So that's usually not even shown, which is quite bad. Have that many charges. But does it have the same net charge? What is the net charge? Plus 1, plus 1, plus 1. I mean, it does have the right net charge. So equal contributors here. We stabilize the cation by a pi bond. How about bond below? Draw resonance structures there. You're actually going to be able to do more than one. Tell me how many you can do. It's going to be a windshield wiper. How do you stabilize a plus? Electrons towards it. Okay? Like a windshield wiper. But you can maybe keep going. See if you can just keep going. How many do you get?
9.
How many resonance structures can you draw here? Anybody think they got the total number? If you count this as one, how many more? Three more. Three more, yep. What do we do here? Only thing we can do is these electrons just windshield wiper over. You can't do anything here. There's no, you can't move up a pi bar. If we do that, what does that give? We don't have pi bond there. We didn't do anything with those. What's here? Plus? What next? If we move that back, you just come back over here. But here we can flip that one up. Resonance arrow. So now we have there and there plus here. Now we can take this and windshield wiper it over here. I'll come this way. Plus there. What next? If I move these down, what do I get?
The ring.
Get that back, yeah? There you go, 3 additional other than the one drone. 4 total resonance structures. What is the hybrid going to look like? See, these are actually all fake structures. The true structure is a blend of all these where the electrons are really just smeared or spread all the way through there. Hybrid is going to have, tell me this, how many p orbitals are we dealing with in this pi system?
3.
How many p orbitals in the pi system? 7. Yes, 7, right? You don't see 7? 7 p orbitals? I mean, doesn't every carbon in the ring have one? Doesn't this one have one? Here's your 7th one. What's the hybridization of that carbon? How many H's there?
1.
There's only one H. That makes it a plus. It's carbon with only 3 bonds. What's the hybridization? sp2. What's left over when after your hybrid's on sp2? P orbital. And it's empty. That's why it's a plus. If you graphed this during week 1 or 2, wouldn't you have gotten that? It would have been sp2 with a p orbital. What type of bonds do you see that carbon here making? Bond to carbon, and a bond to H. Because there is an H there, and then empty p orbital. I mean, if you draw it localized, you got 1 electron all the way around. Pi bond, however, 3 pi bonds, but it's really all there. But see, this is all conjugated too. We're showing that with these resonance structures. So we got 7 p orbitals. How many electrons in the system? 6 pi electrons. 2, 4, 6. There's not one there. That's why this thing is a plus charge. 6 pi electrons spread over 7 p orbitals. We're showing the resonance structures. The hybrid. Let me get rid of some of this. The hybrid's going to be like this. I want to come inside the ring. Is that single bond between here? No, it's got some double bond character. We see that in the resonance structure. So that's somewhere between single and double. What about here? Let's single there, single there, single there. We never showed a double there? That's because this really doesn't give this, does it? It's actually another structure. Because if we move that here, it's the same thing, but this is your benzene resonance. That right there specifically gives, I mean, that's putting the pi bond here, right? Here, nothing moved there, so that would be this. But see, these are what?
Different.
These are just resonance structures, though. But to go from here to here, you don't move the cation. You would do, you'd bring this down, you'd move that up, and you'd move that there. So that's just the there. You got that joke? The find resonance. You see how the two benzenes are drawn with the pi bonds differently? Which one's correct?
Both.
You draw either way you want. It's really the other way around. It's really this. So that's really a resonance structure. But you can say, going from here to here, you don't delocalize the charge. So a lot of times you're asked, show resonance structures where the charge is delocalized. That is a resonance structure. Last thing here, this is a very common cation. The carbon that's bonded to the benzene ring, that's called the benzylic carbon. And thus this is a benzylic cation. Those cations are very stable. Why? Resonance, because the charge is really delocalized by resonance all into that ring. It's a very stable carbocation. On the other hand, look at the big difference in cation out there. How stable is that cation? Is there any resonance here? No p orbital here. I mean, you got p orbitals all around here, not here. And so it's like isolated. That's isolated from this. It can't do the resonance thing. It's a very bad cation. Here, all you can do is maybe help it out by doing, making it tertiary. But you can't do resonance with the ring. Benzylic cation is a good cation. Always look for benzylic cation. Another way to stable plus charges is with lone pairs. So when you have a heteroatom that has a lone pair, I think we saw an example or two of this when we were looking at cations before. You draw a resonance structure of that where the charge is delocalized. These electrons can do what?
Make a double bond.
Make a double bond. How many lone pairs on the oxygen now? There's one. Where's the charge?
On the
The
other.
oxygen.
Because if that's plus, the resonance structure has to be plus. Oxygen is now plus. We stabilize the plus by moving electrons towards it. We can do pi bond, but we can also do lone pair. Charge has been delocalized onto the oxygen. There's a resonance structure. Which one's major? Left or right?
Right.
Who votes this one? Who votes this one? Everybody raise their hand. Everybody. Good. That one. Why?
The double bond.
Because it has more bonds.
What about the charge?
What about it? What's wrong with it?
It's on a more electronegative data.
It's on an oxygen, yes. That's one where you could say, well, you don't like that, okay? But having more bonds beats that. It all has the same number of sigma bonds. This has no pi bonds. This has one pi bond. We made a new bond. That's going to make it better. Here's the take home. It's golden rule number. It's right there in the middle. Your electronegative heteroatoms like oxygen, nitrogen, and your halogens, it's okay to show positive charge on them and to use them in resonance like this, as long as they maintain an octet. Does this oxygen have an octet? Yeah. It does. 2, 4, 6, 8. It has an octet. It's okay. It's okay to show the positive charge. I'm not just making this up. The evidence from the lab supports this. Okay? Don't ever do this, though. Don't ever show an oxygen or a chlorine or a nitrogen in resonance with no octet. All right? It's on the golden rule. If it has no octet, well, you'll be in trouble. The atom will hunt you down. It will not be happy. It's okay like this. This is major. That's your major resonance structure. This is minor. That is the blend. If we drew a blend, it would look more like which one? That one. That is, the charge is more on which atom? Yeah, that's what major means. It has the major characteristic. This is sort of like the kid came from mom and dad. The kid looks more like mom. Mom's prettier. Mom's more stable. Okay? But the kid still has some characteristics of dad, just not as much. Okay? See here, everything has an octet. Even the oxygen. Here the carbon doesn't have an octet. Okay? What we just talked about, when we get to organic 2, October 22nd. Okay? We'll do lots of that in organic 2 because we'll do lots of resonance structures with heteroatoms. Question?
So if you do this with if you're creating an alcohol, is it really going to be more stable because this fuel is only a little bond? Is it?
I didn't hear about alkyne.
Like if you're like throwing an arrow to create an alcohol,
To create an alkyne, you have to show me on paper. Draw it out and show it to me. I don't know how you make an alkyne.
nothing this way.
Yeah. Draw resonance structures of the compound below that illustrate delocalization of that positive charge. Of your resonance structures, indicate which one is major. Also, how many p orbitals are in the pi system and how many pi electrons are in the pi system? How many p orbitals in the pi system?
4.
4. How many electrons?
Also
4.
4. Yes. What's the hybridization of the nitrogen? T? What's the hybridization of the nitrogen? Not sp3. What do we say? Anytime a lone pair is next to a p orbital, a lone pair is going to want to be in a p orbital. Remember that? Is there a p orbital here? Yeah, it's sp2 with an empty p orbital. Down here, no? You got no structure. We've already graphed that earlier, right? We graphed it right here. There's an empty p orbital. If we draw the p orbitals, what do we got? You all know there's a pi bond, right? So there's two p orbitals there, one electron, one electron. There's a nitrogen. There's an empty one here. It's sp2 with an empty p orbital. The nitrogen is what hybridization?
SP2.
sp2. Why? Because anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. And there you go. And what do you got? You've got 4 p orbitals conjugated. How many electrons in the system? 4. 1, 1, nothing, 2. But those 4 are spread out in there like 4 quarts of water in a garden hose. That's the true structure. We can do that with the fake resonance structures, because these are easy to work with. That gets a little cumbersome. I can move this here like a windshield wiper, and I could get boom, boom, boom. You'll see that? Got that light dark there. Everybody get that resonance structure? How about another one? Not from here, but there could be another one from here. I'll call that A, and that's A. What can we do here? We can move these in. I'll call that B, and we'll go here, B. What does that give? Okay. Anything wrong with any of these?
The positive charge on the end.
All resonance structures have same net charge. That's positive, that's positive. Uh-oh, where's my positive?
Nitrogen.
Yeah, that's a positive nitrogen. It's got 4 bonds. No lone pair. Which one's major? Here, why? More bonds. 1 pi bond, 2 pi bonds. More bonds, more stable. Even though the nitrogen's got a positive charge, and nitrogen doesn't like positive as much as carbon because it's electronegative. It still is a good team player and will donate its electrons. And what's another way we know this is major? More bonds. What's closest? One of the closest ways to seeing compounds in the electrons? X-ray crystal structures. Yeah, a lot of X-ray crystal structures show the electron density distributed more like this. Kind of not as easy. I was going to say which one is best of these. I don't think that's as easy. Maybe a case where we can compare these other two, the non-major ones. There we go. The charge is delocalized. Hybrid, you got partial bonds all the way through here. We can do that real quick. Boom, boom, boom. I do something like this. Partial plus on the end, partial plus here, partial plus there. Kind of something like that. Electrons are spread all the way through there, and your charge is also delocalized on different atoms. Question?
Do you have to like connect all the resonance structures with like, double-headed arrows? It's like, you know what I mean? It's like, see, like that first one goes to
I mean, here?
Yeah.
You could.
But that doesn't do that.
I just move 1 arrow at a time. You can move 2. How can you go from here to here with arrows? Move this here and move these up. Move that here and swing that there. 2 arrows, you could get to that one. Once you get better, you can start maybe doing multiple arrows. But I'm not going to do that. I'm going to do 1 arrow at a time until maybe next time when we have to do 2. You have to note, does this arrow movement give that? Well, yeah, pi bond being made here. This pi bond moving over here. See how it gives that? Just like a mechanism arrow. We're showing movement of electrons with our arrows.
But we don't have to draw all those intermediate arrows, or do we need to?
All which ones?
The last one that you just drew, I guess, the one, the far right arrow.
Well, it depends on what you're being asked. If you're asked to show all resonance structures where the charge is delocalized, you really don't need any arrows.
Okay.
But I would recommend using arrows on your scratch paper or wherever to just get you there. Your arrows is your method, your convenience of making sure that things are right, doing this, you know, as opposed to just kind of just staring at it. It's your work. Process. Got to keep in mind though that this is just us on the board or on paper. The molecules are not pumping in the electrons. None of this happens. The molecule is just this. That's the molecule. Okay? We can go back to pink. Okay, we got a pink sweater. If you're having a hard time describing pink, you can say, oh, it's a blend of red and white. I can show you red and white. Pink is sort of in between. You get it? And that's kind of what we're doing here. We're showing you, three colors, but the true color is a blend of all those. That's just hard to show because it's sort of cumbersome. Question?
So is the reason why we do this is all because like when these react, like the electron density will be like high in an area or like where it's going.
It allows us to predict electron density. It allows us to predict stabilization because if you can delocalize the charge, it makes it more stable. You can also have mechanisms where it starts out like this, but it ends up more like this. And you're like, how did that happen? And the answer would be, it's just resonance structure. It helps us move electrons, and ultimately, it's really a true look at the bonding. Because ultimately, it's not just isolated double bond and lone pair descending. We know that it's really p orbitals and the electrons are on. So you have a better understanding of true structure. And as organic chemists, this is sort of the convention that's been adopted. We show these fake structures. And we say it's a blend, but we call these resonance structures. Let's see what's next. Another example. Okay. Down here, we can predict reaction outcomes. This goes back to our alkene chemistry. Which product's going to be favored if we react this with HBr? We're just doing an alkene reaction with HBr. Which product? The real question here is what? Which carbocation is going to be favored? Are you going to make cation on bottom or top? Bottom. Bottom or top? Who goes bottom? Who goes top? Well, let's show the two cations. We're not going to do mechanism, okay? Pi bond reacts with H+. We can add the H there and make plus here. Or we can add the H here and put plus there. Which one's better? This one. Why? Because these electrons can stabilize that by resonance. So we get pi bond there, UH there, and the plus charge is nothing there. Plus is now on nitrogen. This is a resonance stabilized carbocation. Here's your resonance structure. The charge is not just on that carbon. The charge is delocalized onto nitrogen. Actually, this is your major resonance structure, isn't it? More bonds. We made that additional pi bond. That's better. So that's the cation is going to form. Because the transition state leading to this cation is going to be lower than the transition state leading to the other. At this point, the Br minus then does what? Here's an important thing. You can always work with any resonance structure in your mechanisms. If these electrons add here, what do we get? get this. The electrons can also add to this resonance structure. Always work with any resonance structure. How do we get that? These electrons would add here, and what would happen with these two? We'd push those back onto nitrogen, and that would also give that. Now the bromine is not going to bond to the positive nitrogen because nitrogen would then have 5 bonds. So the outcome is going to be a bond to carbon and push that lone pair back to the nitrogen. You can always work with any resonance structure. Don't let anybody tell you you can't. All right? This weekend when you're watching a football game and it's, okay, they know.
So resonance trumps our rule about force substituting terms.
Resonance, I would say, bumps you up a notch. A secondary carbon that also has resonance is just as stable or more stable than a tertiary carbocation. Even a primary that has resonance is almost as stable as a tertiary with no resonance. That's it, kind of iffy. It's sort of a notch and a half. Hopefully you won't have to decide between two like that. But certainly if you got 2 secondary carbocations and one is resonance stabilized and one is not, which is more stable? Okay. So there we can predict our regiochemistry based on resonance of the intermediate cation. How about down below? I'm not going to work this one out fully. Which one do you think is favored? Why the one on the left? Because you see where you want to make cation? What type of cation do you envision here? Benzylic cation? See, they'd both be secondary, but the one on the left would be resonance stabilized benzylic. And that's where the iodine ends up attacking. So this is our predicted product based on resonance. Okay, now let's look at stabilizing anions. How do you stabilize an anion? Do you move electrons towards it or away?
Away.
We need to move electrons away. I see all the time students having an anion and moving electrons towards it. No. Things want to become neutral. If you got minus, you want to move it away. So we start right here. Draw a resonance structure. See if you can do it. We haven't done one with them. It's analogous to what we've been doing, except we just got charge difference. Can you draw a resonance structure of that? Let's start with the lone pair. If we just move that in there, what do we get? That right there?
A negative charge at the center.
Negative charge on the center?
There's a hydrogen.
It's 5 bonds.
5 bond. How many H's here?
1.
1. Can I do that? Can I have a carbon with 5 bonds?
That was the hydrogen.
No. What do I need to do?
Hydrogen.
Okay. We had the windshield wiper before. I call this the in and out method. Okay? All right. We're going to move these in. We're going to move these out. Here we need 2 arrows. What did those arrows give? Draw the result. You should be able to draw the result of that. I bond here. That's what the first arrow does. What's now on the end carbon? Lone pair, and that's a minus. There you go. There's an H there. I'm going to get rid of it. It's still there. for the in and out. Because you can't have pi bonds with carbon. Which is favored, right or left? This is equal contributor. Can you draw the hybrid? Draw the hybrid. And assign bond order for each carbon-carbon bond. Also, how many p orbitals and pi electrons in the system? These are equal contributors. Can't label one as major or minor. Here you got double bond, here you got single bond. What's the average? 1.5. Here you got single, here you got double. What's the average? 1.5. Here you got minus, here you got neutral. What's the average? Partial minus. Here you got neutral, there you got neutral, so there you got neutral. There you got neutral, there you got minus, so what's the average? See, there's your hybrid. When you look at this, you got to really see that the charge is not just right there. It's here. And the BO equals 1.5 here and here. This bond length is the same length as that bond length. It's a perfect hybrid. Charge has been delocalized. Stabilization by pi bond. Okay. This anion is stabilized by the pi bond, but it's not stabilized by the electrons moving towards it. It's sort of the other way. Which is more stable, that one or this? Which one's more stable? Obviously this one, it's delocalized. So your charge spread out is better than this. Which is a stronger base, left or right? That's more basic. How many over there really wants to become neutral more than this one? So this guy is only partial minus. That's a full minus. That's called a localized charge or localized anion. It's less stable. How many p orbitals in the system? 3. How many pi electrons? 4. Got an extra electron, that's why it's a minus. Why is there 3? We draw the orbitals. We've got 1 electron each pi bond. There's a lone pair here. But anytime a lone pair is next to a p orbital, that lone pair is going to want to be in a p orbital. 2 there. There you go. There's your 3 with 4 electrons. Why did we learn that anytime a lone pair is next to a p orbital, going to be in a p orbital? For this reason. There you go. So we can, because that's the truth. Show resonance structures here. That's the anion of a phenol. How you stabilize a minus? Electrons in, electrons out. In, out. Question? I can't hear you.
If you replace one of those carbons with like silicones, you can expand its on its head. Like say that carbon right next to oxygen. Would it be better to have those? Would it be better to have that localized charge?
Draw it out and show it to me a little bit later. I can't quite hear you. Too many Bon Jovi concerts. Did y'all see the videos I sent by email? Yeah. Are they stupid or good?
We should do like that, man.
Apparently at UCLA, the organic chemistry class, they make videos of stuff. Okay, electrons in, pi bond out. Yeah. Make pi bond, electrons out, leave this. We didn't do anything there. Two lone pairs, and that carbon is a minus. We can keep going. Electrons in. Something's got to leave this carbon though. It's already got 4 bonds, so we move these out here. Pi bond there. We moved them out here. Pi bond there. Keep going. Over here. Move these onto the carbon. In. Push these out to the carbon. See, this is not quite connected. That's just me. Draw it. A bit better. You got it? What if we move these here and kick those out? It's going to be kind of like that, but it's actually going to be the benzene resonance structure because it would look like that, whereas pi bonds have just been. It's the same thing. Well, it's a resonance structure, but this is not a resonance structure where the charge is delocalized, though. So if you were asked to show a resonance structure with the charge delocalized, you would not count this because the charge is not been moved. So just doing resonance here, so just understand. Question?
For the second resonance that you drew, when you moved the electrons, the one right after that, when you moved the electrons over into that, and then on the third, why did you draw your double bond back? Does that make sense?
I drew it between these 2 carbons. Electrons are moving in and make pi bond between these 2 carbons.
Okay.
It don't matter which side you draw it on. Usually you draw it inside the ring.
Okay.
So this is the conjugate base of phenol. On the next page, and what you need to be looking at in preparation for Tuesday is acid base. You need to look back at the acid base handout from week 1 and 2. There was one section where we talked about conjugation and resonance, how it affects acid base. It's the same thing. And we said that phenol this is more acidic than cyclohexanol. Whenever you're considering acids, what do? You really consider the stability of conjugate base, the anion. So which anion is more stable? One that has all that resonance that we just did. Is there any resonance here?
No.
No, there's no p orbital anywhere. That's actually sp3, because there's no p orbital anywhere. So this is an isolated anion. This is resonance stabilized. Phenol is about 1,000,000 times more acidic than regular alcohol. On the back is resonance in neutral molecules. We did neutral at the very beginning. It's easier to do neutral when you have a heteroatom. Because your heteroatom lone pair is going to be a source of electron density. As long as that heteroatom lone pair is in a p orbital. Is that nitrogen lone pair in a p orbital?
Yes.
Certainly is. If you had graphed it during week 1, you would have graphed that nitrogen is sp2, the lone pair is in a p orbital. Why? Because it's next to a p orbital. You can thus, this could be a minus. These electrons can move here and these can move out. And you can start showing them. You can use that lone pair for resonance, even though that nitrogen's not minus. You can still use the lone pair. Once you do those on your own, let me show you, set you up. I need you to do the next page or two on your own. Let me just show you. Draw resonance structures, then we can ask questions like this. Which carbons of the benzene ring of aniline above are most electron rich? Those are going to look at your resonance structures you drew, and you'll see there's some of the carbons will be minus. Those are the ones that are more electron rich. With benzene rings, it's often common to have additional groups on the ring. We can do resonance with the ring, but then you have to consider, can I do resonance with the additional group? One of these you can, one of these you can't. Lone pairs here. Of the lone pairs there, there's only one lone pair in the p orbital. Which one is it? That one. What type of orbital is these lone pairs in? If you graph this during week 2, this would be sp2, 3, and a p orbital. What do I see? Pi bonded carbon is made here, here. There's your pi bonded carbon. The two lone pairs are in hybrids. You can't do resonance with those. You only do resonance with lone pairs that are in p orbitals. Okay? That. But in one of these, you can do resonance here, and then you can do it into this pi bond. Additional resonance. Look for that, and then ask the same question there. Down below is a little bit sort of general. And then the back is where we'll take a look at acid-base. The first two we just looked at over here. Yeah. Why is that more acidic? But then don't forget your carboxylic acids. They're actually more acidic than phenols. You need to do resonance over there. Okay? Make sure you understand this. You can actually do more resonance here. There's a big difference between the two. Okay? There's other questions here. Please be looking at these. Okay? Because on Tuesday we'll hit these pretty quickly. See what type of questions you had about these. And then we'll move on to chemistry of dienes, which I sent you that handout by email. Okay, guys, some of you have lab tonight, and seminar tomorrow. Thank you.